Hey guys, welcome back. Second day. We've got Charles and Gay-Lussac's laws to go over today. Again, they were notes from before we left school, but I want to review. We'll start off by going over yesterday's mini quiz and the problem from yesterday's class. They were both Boyle's law, so they were both P1V1 equals P2V2. For the one in your mini quiz, you were solving for V2. And it's all on the notes from today. So if you open those, you'll see 4.0 atmospheres, my first pressure, 50 liters, my first volume, equals 1.5 atmospheres, my second pressure, and my second volume is unknown. So 4 times 50 divided by 1.5 gave me 133 liters from yesterday's mini quiz answer. For the problem you did in class, same setup, only we didn't know the second pressure. Not really any different for Boyle's law, since these are inversely proportional, you just multiply them. 2 atmospheres times 3.5 liters gave me 7 divided by 5, gave me 1.4 atmospheres for the question we had yesterday in class. We've got Charles' law today, and again, when I'm looking that way, that's where my computer with my notes are. They're the same notes that you guys are seeing. I'm into the Google Docs and seeing the same thing you guys are in your notes. So Charles' law was our second one, and it relates volume and temperature. This was the balloon on the hot or cold day. Athena wants me to set up balloons for her birthday party. It was in November. So it was chilly. Take the balloon outside, the balloon shrinks. Volume and temperature are directly proportional. Volume goes down when temperature goes down and vice versa. So with this, remember, we've got V1 over T1 equals V2 over T2 for my formula. And we can rewrite that, if you want, as V1 T2 equals V2 T1. But be careful, because in Boyle's law, we're using P1 with V1 on the same side of the equation. And here, because we cross-multiplied, we're V1 T2 equals V2 T1. That gets rid of your fraction that came from being directly proportional right off the bat. Don't forget your temperature needs to be in Kelvin. Kelvin isn't hard when you're given Celsius. You just add 273. Always got to be in Kelvin. These don't work in Celsius. 273. You'll be given 3 variables and solve from the fourth. I gave you an example here. 6.0 liters at 40 degrees Celsius. And what volume will it occupy at 50 Celsius? Liter is volume, Celsius temperature, so I know I'm using Charles' law. I see I got a second temperature, but need to solve for my second volume. So my first volume is 6 liters. First temperature, 40 degrees Celsius, but 313 Kelvin. V2 I didn't know. And my second temperature was 50 Celsius, so 323 Kelvin. No matter if I put these in the fractions or into the straight line formula, either way, I get 6.2 liters. It doesn't matter. Get a calculator. You can use the calculator on your phone. You can get one on your computer. Whatever you're doing, run that calculation. Make sure you're getting it. Either way, 6.2 liters. Be careful not to get confused if you're on the line one. That's just the same thing I was saying with V1s with T2. There's your, give this one a try for next class problem. It's another Charles' law one, and there's a video. Somebody else talking about it. Go for it. I don't know what you'll get differently out of that, but it's always good to see somebody else. Gay-Lussac's law is our second one. We're doing 2 today. We only did 1 last time. These equations are really similar. So you've got pressure over temperature. P1 over T1 equals P2 over T2. Temperature goes up, pressure goes up. That's why the spray can in the fire goes boom. That's why you got to be careful if you're making the blowtorch with the axe can. Such a bad idea. Not recommended. Not recommended at all. Temperature needs to be in Kelvin again. A gas exerts 5 atmospheres of pressure at 300 Kelvin. Let's set it up. What temperature is needed to lower the pressure to 3 atmosphere? That's nice, and put the temperature value in Kelvin this time. No need to do anything to convert. Since atmosphere is pressure and Kelvin's temperature, I know I got to use Gay-Lussac's law here. And I set it up the same way. I think you can see it. Mine's not showing right now. Give me 1 second. I want to make sure that you can see the equations written out. When I had it in the computer, it wasn't showing everything. I'm opening it in Google Docs. Making sure that your equations show as the fraction form. Loading. It ought to work. So, yep, you can see them set up as fractions then. That was what I was worried about. We got this. So when you're using Gay-Lussac's law, you're solving the exact same way that you did for Charles' law, one over the other, or the straight line form. Again, you're getting P1 with T2, P2 with T1. So there's a Gay-Lussac's law done for you. 5 atmospheres at 300 Kelvin and 3 atmospheres at an unknown temperature. So I solve. 3 times 300 divided by 5 gave me 180 Kelvin. That's code. That's code. Freezing of water, 273. That's code. You got to really cool that gas to get the volume to go down, or the pressure to go down that much. I want you to watch the lab. It's this guy, his voice is silly. It's not his fault. But he uses an apparatus he keeps calling the Gay-Lussac apparatus. I never have seen it before. It looks like a bulb to me. But he's putting it in different temperatures of liquid and watching the pressure change. It's kind of cool. Again, one of those things we can't do in class. There's another video there also, just somebody else working problems, I believe, for this. And there's some bonus content at the bottom. There's something called Avogadro's Law. Never taught it in Gen Chem. It comes up in AP Chem. So it's one of those things I'm like, there it is. Good. If you want to check it out, you can. Basically, it just says the more moles of something, the greater the amount, the bigger volume it takes up. No kidding. So that's what I've got for today. I'll do the mini quiz for tomorrow and work on your problems. Thanks.